Hello, biology students. Mrs. Smith here. Today we're going to talk a little bit about the chemistry of life. And so you might be thinking to yourself, wait a second, I'm in biology class. I'm not in chemistry. And that's true. But chemistry is very, very important to biology. You can't really have biology without chemistry, and can't really have chemistry without biology. So let's talk specifically about all of life to kind of start out. So there's different levels of organization or different ways that we can kind of categorize different pieces of life. So if we start at the very largest thing, we're talking about the universe. And of course, the universe encompasses everything. And if we take a step a little bit closer to home, we get to Earth, and we call this the biosphere. The biosphere is basically every living thing on Earth. If we go down a little bit smaller than that, we start to look into individual biomes. So we're talking about the desert, the tundra, the plains, the savanna, those different areas within the biosphere that have different climates and certain things that are specific about them. If we take it one step further down, we take it to an ecosystem. And an ecosystem is where we're talking about the interaction of organisms with each other as well as the environment. So this is also talking about abiotic factors as well as biotic factors. And if you don't remember what abiotic and biotic means, biotic means things that are living or were once living, and abiotic means not living. If we continue down a little bit smaller than an ecosystem, we are now going to go away from that idea that it is all of those factors. So now we're only going to be talking about the biotic factors beyond this point and not the abiotic factors. So everything above that, you should kind of circle or color green or highlight green so that you remember that's including all of the biotic and abiotic factors. So now we're going to talk about communities. And so communities involve multiple types of species that are living together in a particular area. If we go a little bit smaller than community, we start talking about a population. So populations are all of the same species in a particular area. So for example, we can talk about a population of lions. If we move down smaller than that, we're talking about one organism, like one single lion. And so these ones in red, they're dealing again with those biotic factors. Smaller than a organism, we start to talk about organ systems, okay, like the digestive system, which includes a lot of different organs. So the next level down are organs. If we go smaller than an organ, we start to talk about individual types of tissues, which are made up of multiple cells. And so all of these are made up of organelles. So we're getting smaller and smaller. Really, these are all parts of an organism, and specifically the cell itself is kind of that line for where we talk about something being a living thing. As we get down to organelle and smaller than that, we're not really talking about living things anymore. We're not saying that it's living. We're talking about pieces that then can make up something that's living, but it's not actually living. So then we get down to macromolecules. Macro means big. If you think micro means tiny, macro means large. These are really, really large, complex molecules. And they are made up of smaller individual molecules. And then molecules are made up of atoms or single elements. And so we've kind of reached the smallest point that we know of, which are the subatomic particles. Now, technically, we can go a little bit smaller than the proton and the neutron. We can talk about a quark, but we'll leave that for chemistry class. So really, an atom and the subatomic particles are the smallest that we're going to talk about in biology this year. So all of them together, all the way from an atom, all the way up to an organism, all the way up to the biosphere, and then to the universe, is really everything that we know of that are living things. So let's talk about the smallest piece first. We'll talk about an atom, or we'll talk about a single atom's element. And so an element is essentially made up of only one atom, and it cannot be broken down into a simpler substance. And you'll see that I have this little word below that says CHNOPS. And you're like, oh, I don't know what that word is. Well, CHNOPS is a nice little acronym to help you remember the most important elements in life. Because if you think about those 6 elements, like ingredients, if you put the ingredients together in different ways, you're going to make up every single living thing. So living things all have C, which stands for carbon, H, which stands for hydrogen, N is nitrogen, O is oxygen, P is phosphorus, and S is sulfur. And if you look at this, I really like this little picture because it kind of talks about how carbon is the biggest thing. Carbon is really one of the most important organic molecules, and we're going to talk about that a lot in this first unit. And so they make up, like I said, the majority of all living things. So it makes up about 96% of life, these 6 elements. The other 4% is a mixture of some other things like magnesium, calcium, phosphorus. So phosphorus on here, sorry, potassium, and some other little tiny molecules that help specifically make up organisms. So here are the most common elements in life circled on your periodic table. You'll see the H, C, N, O, P, and S circled, as well as some of those I just mentioned, magnesium, potassium, calcium. There's also sodium on here, chlorine. Sodium and chlorine together make sodium chloride, or salt, which you might be very familiar with. And so I don't expect you to know all of these in the periodic table. We are going to talk a little bit about the periodic table and how to kind of figure out what those elements are based on their position on the periodic table, because the periodic table is a table, it's meant for organization. So when we talk about an atom, or that smallest unit of an element, it still maintains all of the properties. So it doesn't matter whether you have a single atom of carbon or whether you have multiple atoms of carbon, they're still going to have all of the same properties. And this is actually showing you a carbon atom here. And the reason I know it's a carbon atom is because it has 6 protons. And we'll talk in just a moment about how the number of protons actually give the identity to that specific atom. So how do we determine the numbers of protons, electrons, and neutrons? Well, first, we need to look at the atomic number. The atomic number can be found on the periodic table. I'm going to go back just a couple of slides. If you look, it's the number that's typically at the top of the little square on the periodic table. So if you find carbon, you'll notice that there is a 6 above it. That tells me that there are 6 protons because the atomic number equals the number of protons. So carbon has 6. The second rule is that the number of protons equals the number of electrons. The reason for that is that protons are a positive subatomic particle. Electrons are a negative subatomic particle. So the positive and the negatives have to cancel each other out. So if you have 6 positives, you want 6 negatives in order to get a neutral charge. The neutrons, the other subatomic particle, they have no charge. So they're not going to impact the positivity or the negativity of the atom. They're only there to kind of put some mass into it, which is why you figure out how many neutrons there are by looking at the atomic mass. And so the atomic mass actually comes from the number of protons plus the number of neutrons. So if you have the number of protons, you can figure out the number of neutrons. Essentially, kind of think about the atomic mass like apples and oranges. If you take that and you subtract the number of, let's say, apples that you have, you're going to figure out how many oranges you have left. So if you take the atomic mass, or the number of protons and neutrons, and you subtract out the number of protons, you're going to be left with the number of neutrons. Then what we can do is we can start to actually make a graphic of this element, of this atom. And so in the center of the atom is the nucleus. This is where all the protons and the neutrons are. The negative electrons are actually going to go out into different energy levels, and each energy level can hold a certain number of electrons. So the first energy level is small. It's very close to the nucleus. It can only hold 2 electrons. The second energy level can hold a maximum of 8. The third energy level can actually hold 18. But even though it can hold 18, it typically only holds 8. And that has to do with something called the octet rule, which I'll talk about in a second. So if we take this picture, okay, and we're looking at this larger, so we have the number of protons and neutrons, we start to fill in the number of potential electrons on each of the energy levels. So 2 on the first one, a maximum of 8 on the second. And so when there are 8 on that second ring, or we have 2 on the first ring, or even 8 on the third ring, we talk about the element as being stable. So when we have 8 electrons on the outermost ring, the atom is stable. And so that means it's not going to have to get any more electrons. It's not going to have to lose electrons. It's very, very stable. If it's a very small atom, like hydrogen or helium, that only have the first energy level, they're stable at 2. But most elements are going to be stable when they have 8 on their outermost ring, or 8 valence electrons. So valence talks about the electrons that are on the outermost energy level. And so this is what we call the octet rule, or the 8 rule. So again, when you're looking at the periodic table, you can really start to use the information that's there in order to help figure out the number of protons, the number of electrons, and the number of neutrons using those 3 rules. So all you really need to know is what's on this periodic table. The number at the top of the little box is going to be the atomic number. The number on the bottom is the atomic mass, and you are going to round that number. So for example, if you see nitrogen, which is number 7, you'll notice it says 14.007. Just round that to 14. Oxygen, its atomic mass is 15.999. You're going to round that to 16, and that will help you answer some of those questions as we move forward talking about how to figure out atoms. Okay, so that's really important that you look at that element key to understand how to figure out the protons, the neutrons, and electrons. And I'll have a little video for you that goes into a little bit more detail to helping you do some of those problems in the future. So that's just a little start about the chemistry of life. Make sure you filled in those notes, and then you're going to move on to watch the specific video that talks about figuring out the protons and neutrons and electrons, and you're going to do some practice with elements.